Yeah, I don't. Pretty good, you thought? I did. Remember this. Problem.
Yeah. Cool. Yeah, so what I wanted to start with, and this I think actually can lead a bit into some of the conversation on parallel, is just showing you guys the plugin of empymod into SimPEG and what I did for that. So empymod is a 1D solver, but can work with 3D sources. So it does all of the digital transforms and all of that to get the 1D solutions. And so he's got all the forward, yeah. So in frequency and in time, and wanted to invert them using SimPEG. So what we've done is first wrote like the problem in survey class for him to plug into SimPEG, and then use just finite difference sensitivities. So within SimPEG, we generally do analytic sensitivities because it's faster, but for a 1D problem, like his stuff is quite fast, so it doesn't really matter. Yeah, and so what? Okay.
Yeah, Jake.
Yeah. So I'll show you like the first pass implementation of it, and then this morning I was working on generalizing it a little bit. So here we're just setting up some input parameters. So he just defines your depths and then resistivities, which could be anisotropic. Create some synthetic data. So that's what it looks like.
But this is calling his code, right?
Yeah, this is all calling his code. So right now is up to empymod. So that's all empymod. And here, this is now what the SimPEG wrapper looks like. And so we've got an empymod problem, which inherits from base problem. For the first pass, we're just starting with resistivity being the thing that we'll invert for. We can hook up other parameters and make it anisotropic and all that stuff later, but for now, we just wanted something to work. So started with that. There's some settings that you might want to change, so we can turn these into properties on the class. Here. Then there are a set of fixed parameters. These we can again also turn into things that potentially are on the class and you can fiddle around with, but for now they're just fixed. So this guy here actually calculates the data. So right now we just called it calc.fm because that's what it was called earlier. Maybe not the best name, but that's fine. So all this does is calls the empymod with the resistivity and gives you back data. So when we ask for the fields, we just first set the model and then do calc.fm of the resistivity. And so we can expand this out if you actually want to have other variable parameters, because here, like, it's taking all of these things, so we can change those if we wanted to. And then to get the sensitivity, this is using a centered difference, just doing a finite difference. So we just take m and then step to either side and stack up the sensitivity. So it's pretty straightforward. So right now, of course, it's actually calling this explicitly. What I've been working on here is actually building up a utility for computing sensitivities using finite difference, so that eventually, hopefully, we should be able to plug in anybody's forward simulator and invert it. So yeah, a few more like sanity checks and things like that. So defining the perturbation that we're going to take and a minimum perturbation. So this, I figured we probably want to try and do some percentage of the model as a default, but then also have a floor in case your model is 0, so that we make sure that we duplicate it.
Is there a theory in this, like how much perturbation you need to do to be able to get the closest sensitivity?
It probably is. I just threw some numbers down and tested it and saw if it was second order or not. But yeah, that's absolutely something we should look into.
Perturbation.
Yeah, I mean, it started with like 10%, or actually with all the examples we ran, I just was.
Sorry, how do you decide whether it's second order or not?
Doing the derivative test.
Okay.
Yeah. So in that case, it's just like we make sure that basically, if you're including the sensitivity in an approximation to a function, it should converge as second order. So that's how we test the sensitivity. So here, the goal would be that basically we can take any function as long as it takes a vector and then compute the sensitivity. So for the EM prime mod example, we would just wrap that calc fm in like a lambda function or something. And then here, I broke this into 3 pieces. We might want to simplify this in a bit, but you might want to do forward differences or backward differences or centered. Because forward or backward is going to be cheaper because you only have to calculate one extra thing. So those are all options. And then here, like based on whatever your default choice is, which right now I just put the centered difference as the default. This would then spit back the sensitivity. So I haven't tested this at all yet, but this is the sketch of what that could look like. So that gives us J prox. We're going to store that for every model and just clear it whenever the model is updated because we need J and J transpose, and now it's just a matrix. So then JVec and JTVec are just. And then we also needed the survey class. So implemented that with just the number of data and the eval, which is just calling this, which is just calling fields.
So you're always reassigning self-that model, but you never seem to be using it.
Yeah, we are actually using it. So where we use it is actually here. So when I set the model, because it knows that my model is row.
Oh, and it's some of the model.
It does it does the mapping.
Okay.
Yeah. So that's how, like, when we're using wires and things like that, that's how it knows what to hook up. Is like we've told by saying that the mapping is a row map. The list of numbers is coming in as my model is going to map to row. So here, when I set self.model, it takes care of all of that.
Yes, so I was initially trying to do self.row equals m, and that doesn't work.
Yeah.
So why are we taking it from, like, instead of assigning directly to self.row, why are we doing self.model to assign back to row?
Because it needs to go through the mapping. And the model is always the thing, like the model is sort of our, that's the inversion parameter. If you didn't want to invert, if you just wanted, so like in the EM code, frequency domain, we have it hooked up so you can invert for sigma or mu or both. If you on the outside just set mu equals whatever, it's not going to invert for that. So it only inverts for things where you provided a map. Does that make sense?
Yeah.
Feel free to stop me if there's things that come up that are very confusing, because I know we've got our own language that has evolved. Okay, so this sort of arbitrary distinction of the problem and survey also got me thinking about this problem with problem that we've been talking about. And I think it's similar in linear problems where like your fields are really your data because the way that you construct your matrix is based on where your receivers are. So having those two things separate is kind of unnatural.
And we always invert pair, so it's always kind of a substep that And then if you want to change it, then we unpair and pair again.
Yeah, which is super annoying. Yeah. So I think this is my sketch.
But what was your point then? Like,
Or just extra steps, that kind of redundant steps that are not serving any purpose, really. Like, you know, we always need to pair it. And if you want to change it, then you need to unpair and then repair the next one.
Oh, I
It's creating a problem.
I mean, the survey and problem.
In the
Yeah.
problem.
So what I think we should do is combine those as a simulation. And just so that like the mesh, all the survey parameters, all of that go on to the simulation. And each of those pieces can be modular. And what I like about this is we can also play with order of operations, I guess. So for example, a lot of the utils that were built for DC, you know, like build a mesh based on where my electrodes are. If we have everything in the survey class, then, or sorry, in the simulation class, then strapping a util on that just says build a mesh from my survey parameters, I'm going to set those first. That makes sense, and that's easy to do. And same thing, just like I think it gives you more flexibility on what you're defining when. Because like when I'm building up meshes for the casing stuff for frequency or time domain, like you first set all the survey parameters and then decide how far to pad based on my last time or my lowest frequency. So having utilities that like can just touch all of these pieces without having to know if it's paired or unpaired or whatever, be helpful.
What do you think of, because if we do, right now when we load, let's say, an observation file from outside, or just load data, we can create a survey, which is its own container that holds the data. Now, will we create simulation directly from the observed data?
So I think there's two important things that we need to like tease apart here. I think the data class is its own class that we need to then
Create or
yeah.
revise.
So the data has sources, receivers, the data, and then uncertainties. So I think it's a very lightweight class, like data being your observed data. So it is an array of numbers. So from that, you can then build a simulation that is looking at those sources and receivers. Does that make sense?
How do they depend on that survey? Because that's what survey does, it holds that receiver varies in the data. So how is the data dependent on survey?
So data, okay, right now the survey also has extra stuff on top of it. So I think data needs to stay very lightweight and is exactly like sources, receivers, observed data, and uncertainties. That's it. Right now the survey also computes dpred and does all of those steps, which is like, yeah. So I think that the data class is actually just a container for your data. And then the simulation class actually knows how to go in, compute fields everywhere on your mesh, compute your predicted data. And it should not hold the observed data. The simulation should not just feed it. Yeah, you should set up like your sources and receivers, and everything you need to create predicted data is a simulation. And then when we're doing an inversion, you need both your data class, which has your true data, and a simulation, which can simulate that.
Oh, so we're deprecating survey class.
Yeah, so I would suggest that like the simulation, we get rid of both survey and problem.
Yeah, because what I'm not sure is data classes cannot, because source and receiver class is fairly heavy, right? Like that's where you evaluate, you know, this projection matrices, sources, and stuff. So how? Yeah, I'm not sure what's the real difference here, because like that's actually where the most kind of expensive stuff is happening in the survey class, because the source and receiver is attached to the survey class, and then that's where kind of complication, I guess, is coming from. But the what's the real difference between data class and the survey class? Is that you're just deprecating the dpred.
Yeah, so we pull out dpred, and you're not actually, like the thing is we won't ask like we won't be acting on those sources and receivers. The only time you act on them in terms of evaluating them or asking for their derivatives would be inside the simulation class.
So you only get the specs inside
Yeah.
the data class, like, yes, right?
Yeah.
Where transmitters are, receivers are, what their geometry, and never
No.
change them.
Yeah.
Yeah. Then you do your projection inside the simulation.
Yeah.
Yeah. So that way you could also have multiple like versions of say that data set with different say noise uncertainties,
Sure, yeah.
and you can throw that one into it, and then try that one and that one without having to unpair and pair. Is that
Yeah.
what I'm kind of getting at?
Yeah.
So what,
I think, Sonny, the biggest thing here is it's the lightning of the data class, I think, is important. But the biggest thing is removing this need to pair and unpair the problem and survey, and that those should be one thing. Because like for empymod or like plugging into any other package, like they just provide you the entire forward simulation.
Right.
And so us trying to then unnaturally tease it apart is strange.
Yeah.
So maybe this helps a bit. And so, like when you then instantiate this, because right now actually to set up a problem, you have to provide it a mesh when you instantiate it. Whereas this, what we can do is you can fiddle around with what order of operations, like how you want to construct that class. So if you want to set your survey parameters first and then build a mesh, you can do so. Or if we have utilities to create a synthetic survey on a given mesh, you can do the other way as well. Does that make sense?
I think there's still a connection between data and simulation that needs to be done, right? We're not going to be able to swap. Because if you swap data, then all your projections for your receivers have to change every reset.
But so what my suggestion would be in that case is if you're swapping out how your survey is defined, then you just need to update the simulation's sources and receivers. Like when you're setting up the inverse problem, the data shouldn't be changing on the fly.
Now I was thinking in terms of pairing, right? So we're doing pairing right now because we're checking, okay, once they're associated and once the connection is made, then everything's created and everything is set for this pair of objects. Right? So we can still need to do that for data and simulation because.
So in this case, though, the data, I think it's really important to keep the predicted data and the observed data separate and not confuse those two. So the data class, as it sits right now, well, I think it should sit in the future, is just observed data and your sources, receivers, and uncertainties. And so those are all things that you need to then communicate to the inverse problem.
Okay.
And the only thing that the forward simulation needs to know about is your sources and receivers from that. So you create one set of sources and receivers from your data class. And then when you instantiate your simulation, you provide it the sources and receivers from your data class. Does that make sense?
Yeah.
So like, maybe let's sketch this out in pseudocode.
We just create a new simulation that if you have to change the data, you just create a new simulation.
Yeah, so if I have like my data is those bond data. Whatever. Okay. So then here, things that should be on data is we should have data.jobs, data.source list actually, because that then contains the receivers. And then data dot. So this then being your floor, this is your percent uncertainties. Okay. So then, if we're going to create now my simulation equals to pc.simulation. For now, let's just instantiate, like we're not providing any inputs. So then here, my simulation.source list is now just data.source list. Okay, and then we can have simulation and then we'd have a mesh. Does that make sense?
Yeah. No, it makes sense.
Is it,
And if you had to redo after that simulation of source this equals something like data 2, then you would just swap the projections and everything and just recreate the new ones with the new source list.
Yeah, yeah. Because so we're like, you're still keeping all of the information of the sources and receivers. And so if you change where this is pointing to, that's fine. It'll change which projections it's using. And then what's also nice about this is we can also put in some steps that, like, before you actually run the simulation, we validate it. And so here we could actually go and check that, like, the padding is far enough, or that you've got a fine enough discretization around your sources and receivers. And we could throw like warnings or errors depending on how severe something is. So, for example, if you want to, like, I don't think we should kill the simulation if your skin depth or if your padding isn't far enough. Maybe you played around with a few things and decided it's okay, then fine, we should let you run that, but still provide that information. So
your source list would have details about what the geometry of the source is,
yeah,
as well as the locations in which you're going to measure the data,
yeah,
as well as which data are actually being measured as far as, so it's got everything, all the details.
yeah, yeah. So like, in effect, this is actually the survey. The source list is the survey. So that's actually maybe something that we want to rename. Like, maybe it would be better if this was actually, in fact, simulation survey, which contains a list of sources.
If you have a WAV file that's associated with each source, and that's also attached to that.
Yeah. Yeah.
It's waveform?
If you have a transmitter waveform.
Oh, okay.
Yeah.
While we're thinking about this, is there any way that once we have, let's say you would like to switch between frequencies, like run things in different dispatch frequencies and expression, and is there any way we can have switches at the same time, like some sort of combo sources?
Yeah, and so I actually think that by putting everything in the simulation class, this actually should help us parallelize. So do exactly that. It's basically like simulation dot split up by frequency, and then do that. And so then in that sense, like maybe that returns a list of simulations or something to that effect that we can then send out to a cluster and have each one compute separately.
Cool. All right.
Okay. So the annoying part about this is this touches everything.
Yeah.
That's just that. The good news is that you've done your part. That's all.
Yeah, so it's going to be a big upgrade and a little painful because it also touches user-facing code.
yeah, because Well, all the example, it's going to change it. And
I mean, and
probably
it shouldn't be too bad.
yeah, code-wise, it may not be that bad. I think. It's
It's just doing it like.
Yeah. So what?
That should be SimPEG 1.0 after we do this.
Yeah.
Get out of the 0. And then
Yeah.
that's a reward.
Yeah. So to sort of start on this, I'll take a look at the EN code. Maybe not.
Well, I think you'd probably rather like starting from small byte. I guess EN code's fairly good.
Yeah.
It's fairly complicated as well.
Well, the inheritance actually makes it like not too hard. It might actually be better to start with
1D linear process.
Exactly.
Yeah, I'm not entirely sure. Okay, well, I'll give it some thought, because I think sort of the thing to do is we'll come up with one example, and then we can chat through it and make sure it's actually sane in what we want. Because this kind of upgrade, you only want what you want. So.
Yeah, that's a good idea. And give us a format, and then we can all try our specific expertise.
Yeah.
But probably like, just try within their problem. Like within the problem in their survey. So that's what you've got. And you can parse that out with that's.
Yeah.
That's a good sort of example. There's probably additional stuff that you.
Yeah. Yeah, okay, that sounds good. Well, we can give that a try, and because I do think that that'll help simplify how we parallelize things.
Yes, it does.
It gives certainly more options.
Yeah.
Other than, like you said, you can just batch a whole bunch that way. Send it off to clusters or.
Yeah.
And, well, an option, but if you want to process that way.
Right. Well, because I'm working like really hard in these days just to learn a bit more about parallelization and how to like. I think actually just simply doing parallelization in Python is fairly simple.
Yeah.
And there are a whole bunch of options. You could do empymod. There's multiprocessing. Like all the options. It's okay. It depends upon what you want to do. That's fine. But the hard part was how do I put like that into a SimPEG structure. That was really I wasn't really like I was having a hard time how to do that. The simplest example that I was thinking is, let's say you got like there's no connection in 5 different problems.
So they're
totally independent.
Yeah,
Let's say we got frequency domain EM problem. I got 5 frequencies.
Okay. Yeah.
And then like this is each simulation.
Okay.
So I just need to pass
That's the
all the
simplest way.
all the required information. And but how this like all these processing packages structured is like just a one statement, one map that you can evaluate a certain function. So I wasn't really sure because like what I want to actually pass with a full class.
Yeah.
And then it spits out the information's out.
Given that.
Right.
That I guess that path that you fully go on. So there's a few ways. I'm trying to see if I'm formulating this correctly. So your question is how is it structured that it passes the same information? To each one of them? Or?
Yeah, passing same information is fine, but for instance, we got at least 3 information to be output.
Yeah.
Let's say predicted data, sensitivity vector product,
Yeah.
and the adjoint.
And that's from each one of your.
But it's yeah. So I think if I define that as 3 different things, then that's totally fine. I think that's fine.
Yeah.
But then I need like whenever I compute that, I need to kill that, right? Like because I am looping over. Let's say I got 100 frequencies.
Yeah.
And I got 10 processors. I cannot really store all of 100, right? So
Why can't you store all 100? Because before so once you tell it to start parallelizing, it does a lot of memory management in the background.
Yeah.
And before you start the parallelization, you should have already designated how much. So I guess, say the first thread, you're going to have a vector that comes out of 100 units or something like that. And then you got that for the next one and the next one and the next one. Before it actually starts the parallelization, it will reserve in memory those vectors from each one of those threads, and it will output into a structure.
Yes, I totally agree with that. So I don't know if I totally. You're thinking about MPI. But yes, I think if I write a script, there's no problem. Yeah. But so let's say problem one, it has the functions, and then it takes the whole bunch of input parameters, and then it has predictive data. You need to do a simulation, and then you need to compute the G back and G with that. And you got PI, and so on.
Yeah, and each one of those are going to output this.
Right, exactly. Exactly. And then you just sometimes you need to just stack them over or sum them all of that. Or
so you're going to take all the solutions and then sum over all of them after.
It depends upon the operation. So predicted data, I'm going to stack that over, right? Like, okay. I don't want to sum them.
Oh, okay.
This one probably need to
that would mean sum over.
This one I need to sum it. I just
okay.
Yeah.
So what you would do is you would call. So it wouldn't be P1 bracket. It would be your parallel problem, and you're going to put parameters.
Right.
And you would have to designate your output, you would have one output that would have, say, the equivalent in MATLAB is a cell. So this cell will have your predicted, your
right.
And so then you would just, you should just be able to write, I just want to take the JVec from my solution from this parallel problem and sum over them.
I think he's talking splitting and then sending him to two threads.
Oh, you mean using that information from one thread and then putting it to the other?
Well, somehow having a wrapper around it that handles the output of all the individual threads, right?
Yeah, so that's how you would designate your call, is you would have that output and then equals your whatever you're trying to do with your parallel problem. It's all encapsulated into one. So it should just output your one variable that will have all your information from each simulation, or not simulation, each function time.
Yeah, so, okay, there's complication of I have, because.
Okay, yeah, let's start there.
Because, so I got let's say I got a global problem, I have 10 frequency, and I instantiate each problem for each frequency. So problem is a class, it's a container.
Yeah.
And it's a survey, so let's say we got a simulation, and we got 10 simulation, and that's the kind of,
that's parallel.
That's
you want to run all 10 simulations at once.
Exactly.
Yeah.
But it's just what I'm not sure, because that class has methods in the class, and it actually shares with the global problem. So that's the part I wasn't.
So you're just going to have an array of all those classes,
So,
and each one of those.
no, go ahead.
And each one of those should have all your methods and everything. It'll just make a copy of it.
Yeah, that's.
So you should still, be able to use all the same functions. It's just that problem for that. So problem one will have its own cell, which is its class, and give you all available methods.
And okay, that's good. That's good. I think that part is kind of fine. But let's say I got 10 frequency, I got only 2 processors.
Okay.
So I run this. It runs 2.
Yeah, it'll run those 2. Yeah, and then it'll just.
I'm gonna do this.
Yeah, it won't necessarily go 1, 2, 1, 2.
Right,
It might go
exactly.
1, 2, but
Yeah.
bounce around.
But so then at the second round, I'm gonna lose all the information about this run, right?
Why?
No, I think I'm not, because there are some part that I'm storing,
Yeah, so
Because like that, this problem was gone, right? Like, it's like, I got, this
when it
is,
goes to the next.
yeah, it's just whatever I want.
Oh, no, it stores those two. So it'll do the two, it'll store it in your output array, or output cell, and then it'll do the next two. It'll just keep filling your solution.
Right. So that's what I output, right?
Yeah.
That's what I output. But the, let's say, like
So it doesn't run two and then output.
because what I'm thinking is in the usual run, I need multiple evaluation for each inversion.
For each problem.
Right, it's probably like I'm just thinking about iteration. Iteration one, I need like a couple of evaluation of predicted data, multiple evaluation of JVAC and GeoSci.
Okay.
So that means I don't really need to regenerate it, but I just need to.
Yeah. Well, you shouldn't have to, like, as soon as it's calculated, you shouldn't have to regenerate it. You can run that first iteration and get all your solutions to your problems.
And then the sum, you do the sum in your second step.
And then your second step, you can do your summing. And then you should be able to move on to iteration 2 and then save all the information that you wanted to, if not the whole thing.
And sorry, this is where I was saying, I think starting at the objective function level
Yeah,
is
that's
easy.
yeah.
Like, that's an easy one to start with, is because we're not talking about like any communication between any of the problems. They're completely independent.
Right.
And so that's just like as a first pass. I know we want to go deeper than that, but as a first pass for getting a handle on this, I think that's where you want to start.
Yeah. I totally got the idea. I was I was just finding an example how
Maybe we
how
can,
that has been done. And,
find something like that and start there, and then we can kind of hash out,
Right.
yeah, what we can do is maybe, see if we can get on the same level of communicating.
Right,
There might be
that'd
some
be
stuff
great.
still lost here, but
That'll be great.
yeah.
Yeah. So here's what I want.
Okay.
Well, let's say in DC, I got multiple lines.
Yeah.
And then I just want to separate it as a couple problems.
Okay.
Like 10 lines,
So
10
you're
problems.
inverting each line, kind of
Yeah,
thing.
and then we're each lines and then spits out all the whatever outputs out.
Yeah.
So that's the level that I want to try at this point.
Okay, that's something, we could try that first if you want. That seems like a pretty straightforward problem, parallelization.
Yeah, well, in this comment is like right. I think we could do that in an objective function level, like multiple, and parallelize that.
And then, then you can branch from, start there and then keep going down.
Yeah, and especially because that's a piece that won't change, even if we we're doing this forward simulation upgrade. Right? The objective function that's not going to change. Or like the behavior of it. We'll change some stuff under the hood, but the behavior of the fact that you can get, like, it evals its derivative and its second derivative.
And if you do it at that level, you can do all of the measure composition right away. Right?
Yeah.
You can parallelize this. This is not a level. You know what I mean? The domain decompositions are just a stack of couple of problems, right? So you can run each of those meshes independently.
Yes. I think if you do that in an objective function level, I think
Exactly. Right away. Yeah. We would get the parallelization right away.
Right.
Yeah. And then like what's cool about that too is from the simulation side of things, then like having a util that just knows how to split up the problem in the same way, like for the frequency domain, like split it up by frequencies, and then just like create the reasonable objective function that then parallelizes it. Like that's an easy step. So.
Sorry, I understand. If I understand right, you would split different simulations for each dependencies at first. What you said?
No, so like you create your one simulation as you just normally would, and then there's a util that just says like split this up smartly, and then creates your objective functions.
So where would would I just kind of work with one of those examples and try to parallelize like each, I guess there's like that one example for 3D is you have a survey object, a class for each survey line, and then instead of combining it and invert it, you just take each one of those and invert it, and then have your output.
Yeah.
So that'd be, I guess I'm just trying to find a place to start.
Yeah.
Yeah, I could show you like we worked on. I think depends upon where we want to work on. I think if you want to work on combo objective function.
Yeah. Okay.
I think we could do that.
Okay. Yeah. If we can just sit down, you can show me where to.
Yes.
So,
But your multiple lines, you can just write that as combo objective.
Yes. Yes.
So actually, where it's happening is in so in minimize, basically like this step. Wait,
Where is the function?
oh no, it's in here. Yeah. So here actually is the place to look because this guy. So and it's inside in problem.i. So yeah, okay. So there's a couple places to look. So what's going on here? We're setting the phi d's and then phi. Yeah, there's another level. Sorry. So okay, so this is like where the outside step is happening, and then inside of the objective function is actually all you should really have to do. So here, all this is a list of objectives, basically. And so the step that we can parallelize is then, there's a few places. So like this loop, basically, this guy here. So all this is doing is looking at the list and saying, please evaluate each one of these things, and then sum them up. So this guy, and then the derivative and the second derivative are doing exactly the same thing. So these are where to look, because if this is just now parallelized, that
Well, the misfit and the regularization are parallelized.
Yeah.
Oh yeah.
Yeah,
Okay.
because they're all calling the same function.
Yeah.
Okay. I see
Yeah.
what you mean. Okay. Cool.
They're both built from this base combo. So
Yeah.
That's right.
What makes it complication to me? Because it looks simple, but under the hood, there are a lot of things going on. And how do you actually really pass that information? It's like you really need to kind of explicit about passing that information to your worker.
Yes.
So that's where I'm having a hard time, because although that's an objective function, but below that objective function you got a mesh, you got a problem, you got a survey, and then that all of those information that needs to be in a certain container and then need to pass to the worker.
So the thing that we need in order to do that is to be able to serialize all the classes. And so that will come with properties. So we can serialize the mesh now. The simulation, when we actually do that step of now implementing the simulation, we will be able to serialize with a few upgrades on the sources and receivers. So that's the important step, is to be able to just serialize everything, and then we can send the class.
Right, and
What's the issue side now? Because technically they're all occupying separate memory. What's the conflict then?
Yeah, in theory, there's no conflict. I wasn't kind of just sure how that's done. It's
Under the hood, are they maybe using pointers? Because then it's just, you're just passing pointers and they just know where to access that data. It's only stored once. But when you send it to the parallelization, it's just, oh, pointing me here, grab that kind of thing. I'm thinking that's more or less what is operating underneath the hood.
As long as they're not storing stuff in the class, right? Like they would be changing the class itself.
Then there would be an issue because, well, if this one was trying, yeah, if this one changes that class, and then this one goes to grab that information, and it's not there, yeah, you're gonna have a bad time.
But I don't think when
That
you're
won't
solving,
happen
we
then.
never change it.
Well, if they're independent objective functions,
Yeah.
they're not going to talk to each other.
But you can also write parallelization so that it's kind of like a race. You know, if this one can't do anything until this one does it, it'll wait until this thread's done, and you can ID it that way. Again, it's sometimes that just slows everything back down to, might as well just do it slow. In certain cases, it can speed up.
But yeah, since it's selecting at that level, they're
They're
Yeah, this
completely
level,
different
it's just,
things.
yeah.
so.
What did you mean, Lindsay, when you said we could already serialize like objects?
Oh,
Does
so
that mean I can just pickle it, save it, and then load it back? I should be able to load it back in?
the way to do it is there's now a mesh.save option and a utils.load. And so what that does, you can, it just serializes the important pieces, like the save serializes it to JSON, but you can send it to whatever, HDF5 or whatever you want.
Does that contain the operators?
No.
No.
That's it. I know you're going for it.
No, and that,
Because I have a problem right now that takes over an hour to form the operators. It takes about 15 minutes to do the whole, 15 minutes to an hour then to do the whole inversion after it does it. So it's spending more than half of its time just forming the operators in my mesh.
so there's two things we can do. Like, one, there's stuff to fix. Two, though, we can save, like, we can save your own. You need to go in and hack around on some things, but yeah, we can.
Because I am like reusing the same mesh for like a whole bunch of different runs with different data, basically. Same mesh, so I can just save all the
Yeah,
operators
so-
once.
What you can do is write just a little wrapper, like create a list, basically give it a list of all the operators you want to save. So give it a mesh and a list of the operators you want it to save, and then just have it go through and save them. We can chat about that. And then, like, to reload it, you then just assign it to each of like the hidden properties. So the cell crowd or whatever you just assign, instead of having it be created. So it shouldn't be too hard to do.
So how does it work if you've got, let's say, multiple meshes, so you're working like in your survey, then you've got a whole bunch of different transmitters and like one different mesh for each one. So is that all kind of taken account in your
Simulation.
simulation resource list?
Yeah, so what we can do in a scenario like that is basically like, it's mappings, like all it is mappings, and like we could do it at the objective function level as well, where basically each sounding is its own simulation. And then you just send them all out and map to the single mesh in the regularization.
What?
So each one would have a local mesh, and that local mesh would be based with like a single transmitter for that mesh, maybe in a single simulation. And you do that one, and you get the solution to that, and you map them all back to the global mesh. So what you're saying?
So, okay, so hold on,
Simulation?
hold on. So what's happening is your model in this case is actually a vector that describes the 3D mesh, right? And then each simulation potentially has its own cell mesh or whatever we're doing. So the mapping to the simulation basically takes your 3D model and it's now going to project onto your local mesh. And then that can evaluate all itself and all the derivatives of t. And so in this case, we could actually do that at the objective function level, where each simulation then is its own. For each sound is its own. Does that make sense?
Let's go back to the simpler problem. Let's suppose now you do a problem.
Sure.
And now you've got multiple frequencies.
Yeah.
And then you've got different meshes perhaps for each frequency.
Yeah.
Is that all handleable at this current stage?
No.
It's handleable.
Well, it could be.
Yeah, it's doable.
Yeah, we got all the
It's not.
pieces.
Yeah, that was, I guess, the problem. I mean,
Yeah.
just sort of, setting up the, forward simulation class, right? You made, and then your meshes are in the simulation part.
Yeah.
Then, the question is, if you're going to have the individual meshes for each frequency, and then ultimately figure out what I'm going to do later on.
So that's what we worked on for, like, let's say, global problem has the global problem, so it kind of contains everything. And then each frequency have a separate mapping and separate mesh. That mapping handles, I got a global model, then that kind of generates the conductivity model for each mesh. So once you got that structure, I think, and so that's what I was working on. And then I was thinking about like having, because like there are multiple levels of parallelization. And so I was thinking about a little bit smaller level, like, okay, I got a global problem that contains all the information and I can parse it out there.
And then parsing that to the parallelizing.
Exactly.
Yeah.
So that's kind of what I want to work on at this point. Because like then we can kind of expand to upper level. Yeah. Because it's a little bit simpler in that level. Because there's some. Because if you look even that code, there's Fi, so that's a field. So that's a field class generated from your problem class. And then that object derivative also calls the other, like same problem class. So there's quite a bit of complication.
So each one of those iterations is calling the same objection function, sorry?
So here,
So
what's happening here? So Fi is the field. So let's say you got a DC problem, you got 1,000 sources, and it generates the potential everywhere in your domain. So that's F.
Okay.
Right, and then let's say we got 10 lines, and then each line have all those potential values. That's F of I. Okay. Right. And then here we compute the sensitivity by using that potential, because evaluating sensitivities require this field object or field array, whatever. Okay.
It's soggy. That too, though, if you split up, like I see that sort of accessing the fields from multiple places is confusing, but at the top level, if each line is just its own simulation, then that problem is solved because it's only one object ever talking to itself, right?
Oh, if you go up a level.
Yeah. So instead of going down and trying to take a problem and then split it up, I think if we start at the top level and then later on we can write utilities that know how to split up a simulation sanely, I think that's going to be a lot easier. So like just thinking about these basically, like each objective function is a completely independent thing at this point, and then we can take problems later on and actually split them up in a clever way.
Okay.
Because if we solve this level, then because every problem there's going to be sort of a natural way to split it up, right? But if it's solved at this level, then the only thing that we have to write that's new is how do you split up NT versus DC versus.
Yeah, most of the things can be handleable here at this level. So. Okay. Yeah.
Because then too, like this, you can, even if we don't have the utilities yet, like you can hack on the outside and get a parallel problem from if this is parallelized.
I see. Okay.
Just to make sure, I'd like to ask about multiple meshes, right? We're talking about combo simulations, right? The simulation is not going to know about all the meshes of everybody. You can split the problem in different simulations. Is that correct?
Yeah.
That's good.
And because like what's interesting in that case is like each individual simulation doesn't care about the global mesh. Like it's actually irrelevant to this.
That's right, yeah.
So
Just
we don't have to
it's
pass it
piece when it's done, it spits it out and it sticks it to the global mesh, but.
Yeah, well, because all we need to do is map from the global mesh to the local mesh. So the mapping is the only piece of information that needs to be
That
passed.
that's right.
So the term mapping we use basically to we consider M, our model, to be the thing that we're inverting for, and then a mapping is any steps that you are taking to get that to become a physical property on a mesh. So if you're inverting for log conductivity below the surface, your mapping then turns that into conductivity and gives you aerosols, for example. So that's mapping. Yeah.
Huh. Well,
What's the status of, because everything on the, global problem is still sitting in PR, I think it's the local problem, PR.
yeah. Everyone works for a problem in a single code.
I'm sorry.
It's worked for like a for problem. So I could do a deep graph, and then it has a multiple problems, and then spits out that predicted data.
Okay, inverted on it, inversion works.
For this one, I think you have an example, right? You got a multiple match.
But that's what that's what I'm asking you. Because you said that yes, we can do global problems, but I don't think it's in the content. I don't think it's a framework. Yeah, it's still
I think all we were saying about is like conceptually we can do
Yeah.
it.
Well, I said no, it's not. It's not possible yet. Conceptually. Not quite true. Actually, it doesn't work. We just need a mapping, and I think I have a mapping that can handle it.
That's what I'm saying. It's the local problem.
Right.
It's
So
actually
I think
ours.
actually it's yeah we haven't tried for NT, but that helps.
Yeah.
Yeah. So done as an example. So for now.
Can you bring the field? Well, we should bring them. That will help you outside if you can.
Is that though the same as sort of what we're talking about here?
Well,
Yeah.
It's local problem.
Yeah. It's a serial code for that.
Where?
It's getting slower.
Oh, it's loading all of our comments.
Sorry, maps, yeah. File map. So
Okay.
we should, like, if you can comment on this.
Sure. I can put that
It's a
on
mapping.
the list.
It's basically just a mapping.
It's just mapping. Okay, cool. And then, what is the status of other things? This self-pull in is just docs and like how to install, which is helpful. But then, yeah, what is it? I guess Devin, you're ready for review on this one.
Yeah, that would be a good time. We've got all the errors that show up for code, see all that stuff, but it's not related to the things that I've added.
Okay,
So,
cool. And then Soggy, the DCIP.
Yeah, that's good to go. I think it's all passing.
Okay.
Yes.
Cool. I'll try and get to those.
Yeah, I could review Devin's.
That'd be great.
Actually, I'm interested. So.
Be great. And then Dom, is this still in progress?
Yeah,
Yeah.
what's crashing on them? It's probably just the coverage.
I think so. Oh, and yeah. Cool. And then on discretize. this guy ready to go? I added. Oh, yeah, it was just the comments. If somebody can just respond, just so we have these commented on, because I know we talked about it's not working for random tree, but it is at least tested on non-uniform. Yeah, and then we can pull it in.
The uniform tree statement just meant that the cells had the same size in each dimension. So they were cubic cells, but there were still lots of different cell sizes within the mesh.
Yeah, but like, is it being commented out because it's not working on the random tree?
Oh,
I mean, our order of conversions was definitely different.
oh, so it didn't work for random tree?
Well, I mean, we tried it, but the order of conversions was not the same, so it wasn't a uniform one.
Oh, okay.
I don't think. I mean, this was 4 months ago.
Yeah, if you don't mind just taking another look and then just give a brief explanation as why we're not testing this anymore would be helpful. Yeah, and then we can.
I don't know if any of the other tests run on a random tree or not.
They should, because this is what I believe this line used to actually test both of these. So it's worth checking. If we're changing our test coverage, that's an important thing.
I don't think there was a test to begin with.
No, but on there's other operators that are tested in this file, and they used to be tested on both.
When I built this test, I copied the test from a different operator. And the operator I copied it from already had that line commented on it.
Okay.
So I'm not, at least the one that I mimicked this test off of, I don't think it was running on a random tree.
Okay.
So I would have to look. I'm not positive we're doing that on.
Okay, well, if we can follow that up, that'd be.
So what exactly do you mean by uniform tree and a random tree, and what tests are you doing?
So these are all testing convergence for the tree mesh operators. So a uniform tree, I believe all the cell sizes, like it's the same in every dimension, and then it discretizes like uniformly. So everything is like fairly straightforward, so it's all factors of 2. The random tree, what I believe is going on is the underlying mesh is different, so there's different cells widths in each dimension. So you don't actually, like H is not the same for all of them. And then so it refines and has like stretched in some and not in others. And so what it should be testing then, like both of these should be second order if all the operators are fine. So yeah. For the regularization, like I think it's fine if it's only first order and we're seeing improvement. It's okay to bring in and then it's something we can fix later. But yeah, it would be. Are there any other things you guys want to go over?
Actually, something that does last week, some of the processing tools. I do have some of my code here, or some stuff that we can, just kind of what we would want. Because I've got most of this, I prototyped in Python, so most of it's already kind of written and tacked together. I'd have to make it nice, but so I can add in most of that. So it'll be all time series.
That'd be great.
But how do you want to build? Do you guys have specific files, or is it just, should I just build it that you just take in a vector, and then it operates on it? Or, like, how do you get your data in, I guess, is what I'm saying. How do you want to use the data? Like, you're taking it from, I'm guessing, a binary file or a text file.
Yeah, we treat data like data as a vector.
Okay, so just we'll start from there, not trying to, I guess my question was, it's just, okay, I got it clear. Did you want me to write like a loader?
functions as well, a loader for binary data or text data, or just start building the functions, that, assuming that that's all that in there.
Well, I think as a first shot, if you have a specific format, we definitely need that.
Yeah, exactly. Well, that's what I was wondering, like, what kind of files are you guys working with, or is this something kind of just you want built now, and then, as data comes in, just, build specific loaders?
Yeah, I think as data comes in, we can build the.
Okay, so yeah, I've already got a loader for our type of data, so I can add that, and then I'll just generalize the functions so that
We got a processing.
Yeah, we do
have.
Yeah, I was looking last night. I noticed you guys had a process.
Yeah,
there's
There's nothing in it.
well, there's a processing package, and there's really nothing in it. There's like a sketch of some ideas in terms of issues. I think we laid out just a couple of sketches of things, but there's really nothing in here, so you're more than welcome to push stuff on.
Yeah, perfect. Yeah, I can start that stuff here and there. Because again, I have it all written. It's just have to make it nice.
Yeah. Oh, that'd be great.
I mean, things that work for you are probably actually, going to work for a lot of other people too. Definitely.
Okay.
Use that as a first, as a strong man and see if that works. Or you need to refactor things good. That sounds great.
Yeah, perfect. Yeah. So the processing flow as is it will take a time series and it'll operate either Helverson stacking, ensemble stacking, or statistical rejection.
Oh, cool.
So you got a bunch of stuff.
So that's for like a DC, right?
Oh, sorry, this is for DC.
DC, right?
It also does it'll also work on 100% duty cycle stuff. So if you want to take the harmonics or anything like that, it'll calculate that out as well.
Oh, nice. That'd be great.
If you have a example data set and how, just a simple example that how that processing has been done, just for a single time series, that'll be kind of.
Yeah, sure. I do have the code here. You just want to look at it, or do you just want me to just post something?
Yeah, I mean, if you want to give us
it'd be nice to look at it, and then if you've got it here.
Yeah, it's the kind of wrote for the DS processing, so there's a bunch of stuff that you can ignore. But
do you have HDMI or
VGA? Actually, I have DVR.
This only goes so far.
So we've got stuff for you. So I could do feedback and feedback.
Yeah, exactly. Thanks.
Yeah, paralyze it. No, I'm paralyzing
There's pretty
Good old fractals make for good images.
I just said a lot about it.
Okay. Oh, it's never had such a big screen here. Yeah, so this is just our main page intro. Yeah, nothing too fancy with the parallelization in this code because we have a source and a whole bunch of dipoles, so just simple parallelization, work on all the sources kind of thing. So it's just a simple parallel for loop. And then, specific things for second electrodes. And then again, so with DS, we got to do some subtraction of the time series. So this chunk is, just mostly subtracting. Or, sorry, organizing the data. So you know which node teams with which node and source. And then down here is where the magic happens. This is where it actually just makes. So I've got how it's structured is we have things called patches, which is what would be like a line or like a survey day kind of thing, and then patches hold readings, which would be the equivalent of your sources. And then each source has another subclass of dipoles. And so right now, we're cycling through all the sources, and we're going to initiate a dipole. And to do that, there's some DS-specific stuff here. We do the subtraction so that we actually end up with the time series that we're dealing with. And then we do a little bit of syncing. Okay, sorry, when the subtraction is done, we sync the time series together. And then we get into stacking, which is done here. And I just used this one, using the array fire. So essentially what's happening here in the code is I'm taking that one big long time series and I'm finding so it's a 2-second time base, so 600 samples is going to be your half cycle.
Yeah.
And I take that whole vector and then I do some mod dimensions to make it into a matrix so that each column of the matrix is a half cycle.
Right.
And then it's also creating your kernel, stacking kernel, which is just, well, a brute force one is just, it's kind of like a bell kind of curve. And then if I've also allowed it so that you can play around with that, so you can use different type of windowing to get, so that you can knock out frequencies, undesired frequencies, lower to your source one. So in that case, yeah, I have all the options, just I think 4 right now. Yeah, just a Hanning, a Helpers, and a Kaiser, and a Chevy. Nothing too fancy, but it seems to do the trick pretty well. So what's that? The third part of the code.
Just like, so you take a very long time series that's got full duty cycle or half, right? And then you parse it out into half cycles.
Half cycles, yeah.
Right? And then you put all that into a matrix.
Yeah.
And put the signs on every second or something.
Yeah, so that's done in the filter kernel. So when you build the filter kernel, you it's not just, I guess, your bell curve. Every second node or tap is a negative.
Yeah.
So that gets rid of your linear drift and corrects for your polarities.
Okay.
Yeah.
So now you've got this great big matrix with half cycles, essentially, and now you're going to take each of those columns and start to.
Yeah, and then we throw this filter kernel at them, and then so when you do the matrix multiplication, it ends up with just 600, or sorry, your vector that's the size of your half cycle, and that's all averaged and stacked, and hopefully all your noise also removed.
Right.
In a perfect world, you know.
And do you stack uniformly, or do you stack with a tapered window, or?
So this one is just uniform.
Okay.
The ensemble stacking, I use a weighted stack as well, and it's not trying like just a nice little curve, I guess.
Okay.
More like a Hanning window.
Yeah.
I typically resort to a Hanning window. Yeah, and so the rest of them are all just following the same code, just doing some fancy mod dins and simple matrix multiplication, and you end up with.
And you have uniform sampling over that whole time series.
Yes, and if the sampling does go off, it's corrected for in some of the pre-processing. But ideally, yeah, I'd say 99.9% of the time it's on. But sometimes you'll notice that one, and it's like, oh, you'll see the note, you look at the time series, and all of a sudden it goes back like that, and they decided to go time traveling. So
I'm kind of new to this concept or how you guys are doing it. So you've got basically each row is sort of an individual reading, like an individual shot, you would say. And when you're stacking them, you're taking a weighted average of the values of each of those rows.
Okay, sorry, it's not a source per column. It's
it's a repeated measurement, right?
Yeah, sorry, yeah, it's each one of those half cycles in the column. Yeah.
It sort of seemed like when you're stacking all of those, you're taking a weighted sum of each of those rows or columns.
Oh, sorry, yeah. So that's kind of what that bell curve is doing. So your first couple cycle or first 2 to 3 cycles, and your last three cycles will be weighted a little bit less.
Okay.
Because they're on the edges of that little taper. So it's mostly I guess your heavily weight is going to be your, I guess, center of your signal kind of thing.
Yeah, so I guess that weighting is sort of pretty sharp at the edges and then fairly uniform.
Yeah, so that's the brute force one. It's typically just straight and then 2 little curves right at the end.
Okay.
Whereas if you start multiplying by these little Hanning windows, then you can start getting a little bit more relaxed curve, and you can focus in on some frequencies that you want to knock out. For example, we had one where there was a 7.5 hertz. It's like, what's causing this? Where could this possibly be? And by using I think it was the Kaiser window with a really relaxed side or relaxed taper size. Yeah, it seemed to have knocked it out. It didn't knock it out completely, but it suppressed it. So yeah, it's kind of a cool little thing to play around with. I haven't done all the windows that you could possibly do, but yeah, it's a nice little frequency filter kind of deal. Yeah, so that's just the brute force stacking. That's how that one works. And then, and then again, ensembles works pretty similar, except for in that case, we're just taking that whole signal and we're breaking it up into chunks, and then we do the Paralysis stacking on those little chunks each.
Oh, I see.
And then again, average or knock out the ones that have a bad statistical average or something like that, the rest. And then the second choice, I am not sure where it went for a second here. Sorry, I seem to have lost it in my code. Well, I think about where it is. I'll just continue on from here. So after the stacking is done, yeah, we just do we calculate the VP in the last, I guess this is from 50% to 90% of the on time. And that's just actually, that's one thing I haven't vectorized. I'll have to go back in there and do that. And then we come down here, doing the decays, calculating decays from that stack. I used to have another piece under here that it was just kind of a brute force. It was just doing an average over each one of the individual windows from the decay. Whereas this get taper decay, I'm kind of applying that same idea as with the stacking. So on each window, I'm doing a little bit of a weighted average instead of just summing all of them and then dividing simple average. And I have found that does.
Hold on, this is one period data, right? Like half period data.
Yeah, half period. Yeah.
It's stacked.
Yeah, that's correct. Yeah. And yeah, this code here just takes it. So you've got your decay, you say your little window, you're calculating between, and it just does another little handing at the top. And so it leaks into the other windows, but those ones are weighted so much lower that, I guess when you think about it, you pass a straight line. If you're just averaging them and divided by 2, you're kind of passing all frequencies. Whereas if you give it a little bit of a weighted decay, or if you weight it the same into the neighboring windows, then you're actually filtering out all those higher frequencies that could be in your decay.
It's kind of moving average in time. So good.
I guess, yeah, that would be.
So it's the kind of
as you're going, as you're calculating for each one of them.
You're putting some sort of low pass filter, like a low pass filter, similar.
Yeah, actually, that's a good way to put it. Yeah. I have sometimes a hard time of formulating words, but that was good. So yeah, that's again, I can all this stuff. I've already written in Python as well, so all these tools will have access, so you can even test out.
That's great.
Yeah, if you want to play and see if there's a better way of calculating chargeabilities or anything like that, that's all available as well.
Oh, that's nice.
Now I want to find my stat rejection. I don't know. It should have been right there.
Would it be possible for you to take them apart, because the same handling functions, and we use them for instant processing, right? So
sorry.
You have a lot of nice functions.
Yeah.
If you could just have them as pieces.
Oh, create window or
whatever. Yeah.
Actually, that's what I was going to go to next. I was just going to make it a nice little separate function, so that instead of having it built into the actual dipole builder, it would just call it. Yeah, just be like, I need this, need that, need that. But yeah, again, pardon the code a little bit. It was written in pretty hurried times. That's a new thing too. I've not always been good at that, but I'm working, striving towards. Yeah, just want to go through the stat section here if you don't mind. Take a quick look. Oh, that was a noise recording. That's why. Okay. This is the one I was supposed to. Okay, so current state. Oh, yeah, right here. All right, so in this, the last option is statistical rejection. So in this case, what I'm doing is I'm taking all that signal, and now again breaking it into those little those half cycle chunks, and I'm fitting a Coco curve to it. So it's a little bit of an optimization going on in about around. Oh man, I haven't looked at this in a while, haven't I? Oh no, it's just down here. Okay. I'm lost again. Okay. Yeah, right through here. So right through here, I just give it an 8x8 matrix of a bunch of conductivities and taus, and I just kind of invert through them. Try to test all of them on every one of those half cycles, and whichever ones don't have a good Coco fit, it just knocks it out, and then everything is averaged.
What do you mean 8x8 matrix?
Oh, it's totally arbitrary. It's just a bunch of values that we found were enough of a range that it was fitting to all of our data that we were throwing at it. So it's just a matrix of taus and chargeabilities that go into the Coco equation. And then, so we run through all of those per half cycle to see if we can get what kind of Coco curve that we can fit to it. And and if none of those 8 work, I haven't had that problem yet. I'm sure it's coming.
So you have some sort of fixed Coco parameters.
Yeah. Oh, sorry.
You use that to fit your curve. That doesn't fit, you just reject.
Yeah, and then we just knock that cycle out. So then we just we average in the ones that we want.
Are you using C equal 1 or half or something?
I start with a half, and then I think I just branch out by like 0.025 or something like that.
So you're actually changing C then also?
Well, the next position, when say if those first 8 don't fit, then I'm going to just kind of change that from 0.5 to say 1, and then make a new matrix surrounding that value. But so far, starting at 0.5 in the middle seems to work. Fingers crossed.
But this is after stacking, right?
So this isn't stacking, no.
This is not.
So what this one is doing is it's just taking all the half cycles, comparing them, and then adding them together and simply just averaging all the stats, or averaging all the half cycles, so that you end up with a stack, I guess you could call it.
No, my question is when you're fitting that curve, is after stacking or before stacking?
That's before stacking.
So that's before stacking, and then you can reject that.
Yeah, exactly. And then that's what you're trying to ask. Sorry.
So after stacking first, and then do a statistical rejection. After that, you just get taper decay. So that's the flow.
Okay. So there's 2 different flows. So the first one is you take the time series, you stack it, and then you do your decay.
Right.
And then the other one is ensemble stacking. So you take it, you break the time series into, say, 5 chunks, and then you stack each of those 5 chunks, average them together, and then get your decay. The last one is statistical rejection, which is the whole time series.
Oh, I see.
And it's all raw, and you just cut it up into its half cycle chunks and fitting Coco curves to it, or best fitting Coco curves, I should say. And then average together, and then I think you can call that a stack. I don't know if the multiplication and stuff is the actual stack, but we can call it a stack. It gives you pretty much the same parameters. So these are all tools that I could definitely add. I will have to clean them up. But because like I said, Python is more of my testing everything out. So the commenting isn't as nice. But I will, as I add them, I'll just
I think that's actually where we can play X-ray and mask plane. I think that'll be pretty fun to do it.
Yeah, it's not much, but it
No.
does a lot.
A lot.
Can help you structure it modular.
Yeah.
Yeah. Well, and I think we sketched out a few ideas on how we were thinking about structuring the library. So it would be great, I mean, you have an implementation, if you could take a look at that and just see if we're on base, off track.
Yeah.
If this makes sense. That'd be great. Yeah.
Cool. Yeah, actually, like I said, just one last. So when I started writing that, you want me to put it into the same kind of nomenclature that you're using, like instead of reading dipole, it'd be source and receivers. Make the classes still giant.
That would be
probably makes
Yeah.
sense.
Yeah.
So, yeah. Okay. Yeah, I can do that as well.
Yeah, and I mean, that's something too we can iterate on if you've got something you want to push just to take a look at it. That's really fun. The processing library is very much a playground right now.
Okay. Perfect. I'll start there and then see how it goes. And yeah, I'll take a look at the parallelization for sure. And I guess I'll keep in contact with you for that.
Yeah. But you can see that a lot of the functionality that you've got in DC is so applicable to so many other things, right? You've got airborne data, I mean, it's essentially the same thing, right?
Yeah, exactly.
Different pulses, lots of stacking. So parsing out the kind of basic utilities that you've got, and then just have this
Just make
kind
it
of a
completely generalized.
workflow that script that you just kind of go down and use all of this stuff.
Yeah.
See that working really, really.
That's perfect.
Yeah, if you can have some sort of streamlined workflow that you actually start from your data processing of DC and MP.
Yeah.
And then have got a kind of simple I/O that we can plug that into SimPEG, DC and MP code. That kind of be a cool
all the way
example.
down. Yeah. Go all the way down.
That's exciting.
Yeah. No, by all means.
Donna, any comments?
Oh,
You
yeah.
last?
No.
No.
I mean, I've followed John's work this whole time.
She's helped with a lot of this, like ideas, and
No, more concepts.
I write and.
I don't touch it. Yeah, and then the walkthrough, the code base. I've worked with the version to understand what you're doing. So I'm not on the code from the what you're patching, and I think it's going to be great. The mesh, variable mesh, it's good.
Yeah.
It saves a lot of time because right now it's a key point for us, and we have a lot of data, and we like to play around with them. So yeah, it's great to be able to play around with that. These are a big company, so it's awesome to have flexibility.
That's nice. Sonia asked, was that field school data, was that chargeable, that object?
Not necessarily. No. This was a huge metal.
It's more of a reason. Yeah, it'll show up in resistivity. So I have a field school data set that was collected out in Saskatchewan. It's just like a man-made target, totally open data. You can do whatever you want with it. DS was asked to go and collect some data for their, I guess their undergraduates. So yeah, it's a relatively small 3D data set. I think it's only maybe it's under 100 sources, right?
Oh yeah. No,
Yeah.
It's very small though. It's very a tight spacing.
It's more like an engineering application.
Yeah.
Our mesh can be small.
Yeah, yes. And then sometimes there is a bit of geometry. Lots of coupling. That's. But
It sounds interesting.
Sounds good.
Yeah.
But yeah, it was one that I can
Have
definitely.
you guys run an
know.
inversion with that? Have you ever run an
Yes,
inversion
yes.
with that?
Done that a little bit. It worked fine. Yeah. So
Nice.
we did a lot John was pretty fascinated, but we we have like single receivers, right? So we can create pretty much any type of data we
Right.
want. So when we are in those kind of configuration, we just basically take whatever is convenient for us. That is a very large data set. And yeah, it worked out quite good. Because it was somewhere I can share that with you.
What's that the field school site? What are they looking for?
Oh, actually, it was a man-made target. It's like a big 8 meter by like 4 meter stainless steel sheet.
Yeah.
They just brought in a backhoe and just dug a hole and threw it in there. I think it's on a little bit of a plunge tube, but it's just like subvertical, or sorry, subhorizontal.
Yeah, it's for the students of the US.
Yeah, that data set's good to go.
What else was taken over there, do you know? EM?
I believe there should be some EM data kicking around for that one. DS didn't do it, but I have a feeling Discovery might have done something like that over it. I believe there's probably a MEG data set as well. I can ask for that. But yeah, the DC is what we have access to right now.
Yeah, no, but these are always nice, right?
Yeah.
You got field data sets that are used for schools and open stuff, and
Yeah, exactly.
if we've got the latest equipment that's working on that, and work on that, that's great.
Yeah, I'll make a note of that actually. Sorry. I'll see if I can get that other data set. I would have had it on my computer from ages ago, but that computer's long dead.
Do you know if you've found a lot of IP anomalies that are just associated perhaps with steel pipes?
You know, I don't think I've done enough in the engineering side of things to, have any pipes in our data sets. Like in EM, I've come across that, but nothing in DC or IP.
I guess the reason that we're kind of interested in is just looking at some of the older papers, and if you go back to the 70s, there was a lot of enthusiasm for the potential to use IP for hydrocarbons, right? Because you get hydrocarbons, you definitely get there's sort of a halo. You get magnetite that's in there, and there might be an IP anomaly. So they were pretty excited about it, and then they were realizing, wait a minute, steel pipes have an IP effect. And I guess that was pretty well known 30 or 40 years ago, and Jim Waite and Alex Kaufman and Gordon West and Scott Halliday and all these guys, they're writing papers left, right, and center about IP in oil fields, trying to figure out the effects of casings. And they showed that casings actually had an IP effect. And I've heard that before too, that there's various pipes that have an IP effect. But it was just one of those things that kind of came out and then it just sort of disappeared. But now that it's kind of back on the radar screen and you guys are doing a lot of IP, you might just ask around with.
Yeah, we've had some surveys crossing some pipings, and especially in the US.
Those were power lines, though? Underground power?
No, not necessarily, but sometimes there's some gas pipes.
Oh, really?
Yeah.
Oh, yeah, that one in Arizona. Maybe we do have something.
That was a while ago. And yes, we removed that because because our data that are interesting for our sake, but the client doesn't want to see that, so we just usually remove that. But yes, we've seen that. It's more like a change in polarity, somewhat. Approaching this area, you see EM effect around the pipe.
Yeah, but that might be an EM effect, but maybe not necessarily IP.
Yes. Oh, yes. But you see it in the off time, the way
As this, the oil and gas, has it been processed or have there been patterns to it? In order for there to be IP, there has to be some kind of accumulation by our charge out there.
I think in the these chemical reactions that goes on, there's somehow the possibility that magnetite, at least that's one arrow that is potentially. And there might be others too. I don't really know very much about it. I know that people were really excited about it a long time ago and I forgot about it. And just some of these papers just surfaced over the last couple of days and we're like, oh yeah. And I do remember that people had talked about IP signals due to pipes. And yeah, it's just kind of interesting again to see something comes out of that. So if you just ask around if you've got any leads as to where that may have shown its head. Or
interesting, yeah.
Interesting to follow.
Yeah, we should just look back into the source data.
But that's with a client who probably won't get the data. Surprised they let us have it.
Just some points to tell you where that is.
So that's why the field school data is really nice. I mean, there's good data, and you know what's there, and get multiple data sets over, and then if you handle those, then that means that now you can go to someplace else.
No, you know,
but you need to have something.
Cool. Yeah. And then the arrow data set, Jonathan said that that's okay, but we're just kind of working through it. There's giving us some problems here and there. There's some weird data points that we're still kind of hacking out. So when that's when we get that in a settled state, then we'll be able to. I don't know if you'll be able to post that one, but you guys, it would be able to distribute. Yeah. And then I guess an NDA or something like that.
Yeah.
That's sure. I mean, we're fine with that. We've done that.
Yeah.
For it. And the thing is, then generally, what's happened in those situations, like the data, are confidential. We can't show the results, but we learn enough from that we can make synthetics that emulate that.
Okay.
Yeah. So, but you do need to have good data and a real problem to really make some progress.
Yes.
Good point.
Yeah, and the thing with field school data, I think the IP data were not that great.
No.
So that's like one of the sad part of it.
But you said you had stainless steel.
Just a sheet. No, it was just a. It's more of an it would have been more of an EM target, but it was showing up.
IP from stainless steel. Let me ask our IP.
I prepare that for your defense.
Okay. What about stainless steel?
Yeah, and I want to know that you guys are invited next Tuesday at 4 o'clock.